And so this is a system where you have n grains, and you start off with random noise, and the system goes to the wells and creates the grain boundaries. And the grain energies, and you can see that it looks very much like grain growth. Small grains disappear. You have instabilities with quadrant junctions. They disappear. And you get classical looking, very classical looking grain structures. I want to point out, I don't know, maybe this will pop up near the end, but one of the problems with these models that you should be aware of if you try to actually use them is that, remember it said that you have to have you have a vector order parameter with zeros for all the grains and 1 for the grain of interest. And so if you have n grains, you need n Allen-Kahn equations. And if you want to do 1,000 grains or 10,000 grains, you need 10,000 Allen-Kahn equations, which can get pretty computationally challenging. And so what people do is that they don't use 10,000, they use 100. And then the problem is that it's possible for 2 grains to be right next to each other that have precisely the same order parameter. And what you'll see is that since they have the same order parameter, they don't produce a grain boundary, and it just kind of disappears. And so there's all sorts of complicated algorithms that people have generated, like, and I think it's in the Moose code, where they set out a set of order parameters and they kind of monitor the grains in the neighborhood to make sure that 2 adjoining grains never have the same value of the order parameter, so you don't have this idea of the grain suddenly disappearing at a boundary. The other problem is when you have lots of grains. Remember, one of the order parameters is 1 here. One of the values of the order parameter in the vector order parameter is 1 here, and it's 0 every place else. And if you think about stepping this thing in time, all the way over here, it's 0, and nothing ever happens because the grain sits all the way over here. You're really just interested in the boundary. And so what people have also done is written codes that basically only allow the boundaries to, the order parameters to evolve in certain regions near the boundaries, and you don't worry about every place else to speed up the codes. And so you have, the problem there is that you have to figure out how far from the boundary do you actually have to, is good enough. And that's also another parameter in some of these codes that you should watch out for. But nevertheless, it pretty clearly gives you something that looks just like good old regular grain growth, which is kind of nice. Yeah. So this is where I think the problem is. Yeah. So the question. Yeah. That's right. And if you look at the evolution equations for the models where you constrain it to be 1, they typically put in a Lagrange multiplier to make that constraint in the evolution equation that isn't there in the Fadden-Chen model. Yeah. Yeah, and I don't, as I said, I mean, this took 3 minutes to program up. Maybe the multi-order parameter model we should do too, just to see how it compares. And as I said, this Mullins paper has shown that they in fact get different kinetics for the grains. So let's talk about the effects of elastic stress. Effects of stress on phase transformations. And let's talk about the sources of stress first. One of them is that the lattice parameter can be a function of composition. And so, for example, say that we had a composition gradient in a bar that looks something like this. Composition is a function of bar. And we know that the lattice parameter, the lattice parameter is some function of composition. And so that means that if you go over to the bar here, you'll have a lattice parameter as a function of position that will vary. And so over here, you might have a lattice parameter that looks like this. And over here, you might have a lattice parameter to exaggerate that looks like this. So you have a much bigger unit cell. Then, if you say that the lattice planes are coherent, are continuous, or coherent. Coherent, basically that means that you have to have a continuous lattice parameter from one side, lattice planes from one side to the other. And you can see that the lattice planes expand or contract. And that generates stress. So the assumption here is that these lattice planes have to be continuous. In other words, no dislocations. And it's pretty much in everything I'm going to be saying today, we're going to assume coherent lattices with no dislocations. And so if you think about this problem, it's very simple, very similar to thermal expansion. Generated stresses. Very similar in spirit to thermal expansion generated stresses. But the difference is, one of the major differences is that these stresses can be very large. In the composition case, can be large. And so the best example of this is diffusion of carbon in iron. It's an interstitial atom, and that generates such large stresses that you can actually get dislocation motion as a result of this. And so these can be quite large, so they easily exceed the yield stress. The bulk yield stress of the material. Okay, so that's the first one, and we will talk about this one here this afternoon in terms of how do we add stresses to the theory of spinodal decomposition, and what I'll do at the end of the lecture this afternoon is I'll be able to show you how you can connect these kind of models where the lattice parameter can be a function of composition to the sharp interface model that I'm going to talk about today, this morning. You can also have stresses due to difference in lattice parameters. Between two phases. Between two phases. And this is, they're sometimes called, this difference in lattice parameters is sometimes called an eigenstrain. Eigenstrain, you'll see this used in the mechanics community, or a misfit strain. The simple way to see this is if you take you have a crystal. This is your alpha phase. Make this a little smaller. Take your alpha phase and you take a little region of your alpha phase and you excavate from that region alpha and you put it on your desk, so that size, and then you allow it to transform to beta. It becomes bigger, right? And you put the same number, and then you put beta back in there, and you can see that the beta is not of the right diameter. It's a wrong hole. The hole is too small. The hole is too small. And so what you need to do is you need to compress so what you've done after you put it back in, you have to actually compress the beta phase Okay? And so I want to emphasize this. So beta, and what you're doing here is that you put stresses on the outside of this. This is a stress. And the idea of the stress is to make the beta phase lattice parameter match alpha. And it not only matches alpha, but everything is coherent. In other words, on going through this cycle here, where after I put it back in, I haven't lost any lattice points. The lattice planes are still continuous. Okay, so that's important because what it basically says, you don't have any way of removing lattice sites on going from here to here. Your number of lattice sites is always conserved in going to here, so everything is coherent. And then when you relieve the stresses, I think what's pretty clear, after you relieve the stresses, the beta phase will push out against the matrix a little bit, and you'll get some change in the diameter of beta as it relaxes. So this is the relaxation. Relaxation once the stresses are removed. And so you end up with a situation where both beta and alpha are under stress. Okay? So that the beta phase pushes back out on the alpha, and the alpha phase is under stress. Again, if you look at the difference in lattice parameters in some cases, so you can define an eigenstrain. So the ij here is the ij component of the strain. So I'm saying that it's a purely dilatational strain. It's the same in every direction, and it's the same, and it's given by the difference in the lattice parameter between beta and alpha. Of alpha, and it's can be. So these strains can sometimes be very big. So if you look at carbides and steels, it can be on the order of 20%. And if you think about a metal, how much strain you can put in it before you begin to get yielding, it's about a factor of 10 to 100 less than that, right? So these are huge. These can be very, very big strains. A alpha, yes. Sorry, yeah, A alpha is the matrix, right? Another source of stress is applied stress. And this is very important, for example, in turbine blades, in jet engines. You have a blade that looks like this, and you spin them up, and so there's a uniform stress that gets applied along the direction. And this stress turns out to be very important because it changes the morphology of the precipitates in the alloy and actually changes the mechanical properties of the material. So this is an applied stress. Stress due to centrifugal forces. The last stress that I want to discuss has to do with interfaces. And this is going to be kind of important in the sense that we'll understand perhaps or show the issues associated with phase field models and for stress and what goes on in interfaces. And so there's you can have a stress in the interface. Actually, I'm going to call stress T here. So it could be Tij hat. So it's an interfacial stress. The hat denotes being on the interface. This is the interface. And it's in general, it's a 2 by 2. Oops, sorry. It's a 2 by 2 tensor. Tensor unlike bulk stresses. Unlike bulk stresses. So you can think of a a simple planar case, you can have a 1 and a 2 direction in the plane, and you have stresses that lie in the plane. So there's stresses that are in the plane of the interface itself. And I want to talk a little bit about what these stresses mean and how they differ from things that you might have seen before. Has anyone seen this relationship in any of your undergraduate stuff? Anyone seen that? So this is the Laplacian Equation, and what it says in a fluid is if you have a liquid of phase 1, a beta phase, in a fluid of phase alpha, and if you have a surface tension or surface energy, it generates a pressure. And so you want to think of the sigma or the surface tension like a rubber membrane that's surrounding this liquid and is pushing under pressure, right? And if you look at the literature in probably your undergraduate texts and in the fluids chemistry areas, they kind of use surface tension and surface energy almost interchangeably. In a solid, the thing that's different in a solid is that you can't use these two terms interchangeably. They're different. They're different quantities. And so the surface stress is not equal to the surface energy. It's not equal to the surface energy. And the reason for that, and the reason why they're not the same, is that crystal materials have a lattice. And let me give you an example of that. So consider how can you create interfacial area. And this actually goes back to Gibbs. It's in Gibbs's book. He was amazingly enough aware of this, even though he did not know what a lattice was. It hadn't been discovered at the time. But say you take a lattice like this, right? And you stretch it. You put it under stress here. What you will do is that you will create, and I'll exaggerate, you'll create new interface. 1, 2, 3, 4. Okay, so it's pretty clear that the total interfacial area has changed on going from 1 to 2. So it's an increase area. And it's pretty clear the way you're doing this is by stretching it, right? Okay. The other way you can create interfacial area is to start with this and go to this. Okay. These two areas are the same, but the way you got there is entirely different. Here what you've done, this is by deformation. Here what you've done is you've added lattice sites. And actually lattice planes in this case. And so they're different, even though the surface area is the same. So this process up here, the change in the energy associated with this measures the surface stress. The change in the interfacial area with respect to increasing the number of lattice planes measures the interfacial energy sigma. And so they're different. Okay, and if you think about this simple little analogy here, now you understand why the chemical engineers mix up surface tension and surface energy all the time. Because think about what if you did the variation, or if you did the change that I have up here. So what happens if I take a fluid and I stretch it like this? What happens is that atoms move from the bulk of the fluid up to the surface. And so you create more area by adding more atoms at the surface, which is basically that variation. So they get mixed up together. So in a fluid, these two things are the same. In a solid, they're not. In fact, the surface stress doesn't even have to be positive. And let me give you, the surface stress can be of any sign. Can be of any sign. And so let's say you had, I'm going to exaggerate here, you can have two cases. Let's say this is a vapor, this is the solid. So in this case, the atoms at the surface want to be farther apart. Than the bulk. Bulk in this case, Tij, is less than 0. It's compressive. Or you can have the case that looks up here, like this. In this case, they want to be closer together. In this case, Tij is greater than 0, so it's tensile. So it's not even constrained by the sign. And the reason why I emphasize this is that sigma, the interfacial energy, must be greater than 0 always. So it's like it's like going into your Cahn-Hilliard equations and changing the sign of the gradient energy coefficient to be negative. It's just like doing your spinel decomposition with no gradient energy coefficient and having a negative diffusion coefficient. Things just kind of blow up, right? Same idea. So this can be positive. The interfacial energy has to be positive. Whoops. The interfacial energy has to be positive, but the stress can be either tensile or compressive. And in fact, if you do first principles calculations of stresses in solid vapor solid vapor systems, you can in fact get this effect where it can be positive or negative. Okay, questions? So those are 4 sources of stress. And what I'm going to deal with, we're going to deal with this source of stress this afternoon. This morning, what we're going to do is we're going to deal with this one here, the misfit generated stresses, and these surface stresses. And the applied stresses we'll leave for Guru to talk about maybe. He's done a lot of work on that. Okay, so let's look at the elastic field. Stress surrounding a coherent spherical precipitate. So again, we're going to assume coherency, coherent lattice, which means the lattice planes are continuous across the structure. We're going to assume a dilatational misfit. Epsilon, or the misfit or eigenstrains given by epsilon. You're going to have a linear elasticity, linear isotropic, inhomogeneous elasticity. By inhomogeneous, I mean so that the elastic constants of alpha and beta can be different. Beta can be different. And probably the biggest assumption of all is you're going to assume a spherical particle. So it's not quite a spherical chicken, but it's a spherical particle. It captures a lot of the basics. So if you to kind of step back here, so why I'm making these assumptions is that to do the more general problem of let's say anisotropic elasticity or non-spherical shapes can be mathematically very complicated. Ellipsoids you can do analytically, turns out, for reasons that I'll kind of hint at the end. General shapes, you have to do something very different, like a phase field model. So, but this, I think the idea here is to try to fix ideas so that you understand the basic physics. Okay, so strain is related to stress, to displacement. I'm sorry, to gradients in the displacement. Gradients in the displacement. So if you have some body and you have a point here and you put it under stress, it will move. That point will move to a new point, and it's described by a displacement vector u that takes you from the undeformed to the deformed configuration. And the strain is equal to gradients in the displacement. So this gets into some of the shorthand notation that we'll be using. The comma here denotes differentiation. So u I comma j is equal to the partial of u I with respect to xj. So EIJ is a 3x3 tensor. It's a 3x3 tensor, and it's given by the uj comma I. So the way to think about the reason why the strain is related to gradients in the displacement, because you can take an object here, and if you displace it uniformly, you just move it from one place to another, and that doesn't generate any strain. What you need is that within this body to strain one region a little bit more, displace one region a little bit more than another to generate a strain displacement gradient, and that's what generates the strain. So the stress and the strain are related. KL. So CIJKL is a 4x4 tensor, and these are the elastic constants. Elastic constants. And what we're doing here is the real way to write this equation looks like this. Where you sum over K and L from 1 to 3. So whenever you see a repeated index, that implies summation. Okay, is everyone familiar with that idea? So that's just standard Einstein notation. Some people shook their heads. How about, so is this is that a different equation? No, it's right. Because those alphas and betas are just dummy indices, right? Yeah, okay. That's great. So everyone's kind of shaking their heads. That's great. We're going to be dealing with an isotropic material. And so if you write that equation out for an isotropic material, it looks like this. So lambda is Lamé's constant. And mu is the shear modulus. EKK, remember you sum over so it's equal to E11 plus. It's the sum of the strain. Basically, it's the trace of the strain tensor. Okay. And I won't go through the tensor contraction. So if you wrote outCijkl for an isotropic material and you went through all the contractions, that's what you'd end up with. Okay. So equilibrium. Elastic equilibrium is the divergence of the stress tensor equals to 0, which implies if you wrote this out in Cartesian coordinates, would look like that. So you're taking the derivative of the stress tensor with respect to that same component, so you can see that it's repeated here. Repeated. The divergence of the stress tensor equal to 0. And then if you take this equation here, you take this, and in general, this, you substitute into here. And then for the strains, you substitute in this equation here. And I think what you can see, what you end up with here, is basically just an equation involving derivatives of the displacement gradients. And in fact, for an isotropic, which is one we're interested in, you just get an equation that relates to gradients in the displacements. Second derivatives of the displacements gradients. Looks like that. This is in Cartesian coordinates. Cartesian coordinates. So if you look at this, maybe I should stop for a second here. So if you look at this equation here, you notice you have jj, so that's a sum, and you have I here that doesn't have any sum on it. And so the assumption, the implicit assumption here is that I goes from 1 to 3. So this is actually 3 equations, right? Actually 3 equations. I equals 1 to 3 with those derivatives. So if you wrote this in a general coordinate system, it looks like this. Equals 0. So if you wrote that in a non-Cartesian system, it looks like that. And the only reason why I do this is that we want to write in spherical coordinates. And it's kind of a messy thing, really, quite frankly. But you can look it up in any elasticity book, and I won't do this for you. Because basically the equation that we're going to solve is so simple that you don't have to worry about all these complications, and it doesn't make any sense. So let's go back to the coherent spherical particle after that quick introduction to elasticity. particle. And so you have a particle that sits here. This is an alpha phase. We need boundary conditions. So we know what the field equation is. So this tells us what the displacement. Right? It says the displacement field. You can see that it's second order in space. This is the Laplacian operating on the displacement vector. So it's second order in space. So you need two boundary conditions. And we're going to solve this piecewise. So we're going to solve it inside the particle, and we're going to solve it outside the particle, and we're going to piece them together with boundary conditions at the interface. So this is the classic sharp interface kind of model for this. And so one of the conditions is that the alpha-beta interface must be coherent. And that implies that the displacement is a function of r. So in other words, okay, so what does that mean? So let's say we're using the alpha phase as the reference state, right? And so we take the beta phase particle, we compress it, we put it into the matrix, and then the beta phase particle relaxes. And what it says is that the vector is the vector that takes you from the unrelaxed to the relaxed state is the same. So that point travels here. So in other words, you're not allowed to create a hole. You're not allowed for it to slip. It moves. It's attached from one to the other, and so that's this displacement. All right. So the fact that they're continuous, they're stuck together, they're welded together. There's another. So that's a coherent particle. Let me make sure everyone kind of understands. So this is the coherent particle where they're stuck together. Another model is an incoherent model where, as it's allowed to relax, it can slide. And that's the completely incoherent model, and that's not what we're doing. We make sure they're attached as they move. So this is the coherency constraint here. And the other thing is that you have to have a force balance at the interface. And this looks very much like the Laplacian equation. Okay, so RR is the RR component of the tensor, of the stress tensor. So what it's saying is that you have your Cartesian coordinates here, or 1, 2, and 3. You have a radial vector that's out here. That's the radius vector here. And you have an r hat direction, a theta hat direction, and a phi hat direction. And so TRR is the stress on the r hat plane, which would be perpendicular to this plane here, in the r hat direction. Okay, it's just like the regular stress definition, except here it's in spherical coordinates. So it's a plane. The stress in the r hat plane in the r hat direction are normal, which would be normal to the interface, right? So it's a stress normal to the interface. So if you put a hat on this, it's stress normal to the interface. The other thing that I've done is that I've said that Tij is going to be equal to F (1, 2). And so I've said that basically you have an isotropic surface stress. So it's almost like the Laplacian equation. So in other words, let's set it aside for a fluid is minus P. And so this becomes (2f over r), which looks a little bit like the Laplacian equation. So it's basically the same thing, except expressed in terms of stresses. That's why the change in the sign here, the TRR is minus the pressure. That's kind of a definition that people use. Okay, and so these are the two conditions that allow us to patch the equations up at the interfaces. This is the classic sharp interface model. And now we need far field conditions on the, yeah. Yeah. I'm sorry, say it again? Well, okay. Yes. So this would be F or sigma. Yeah. Yeah. Okay. Oh, that's yeah. Okay. That's right. Yeah. Okay. Let me just put that in so people don't get confused. Yeah, that's the interfacial energy. Yeah. Okay. So you have this excess force. Oh yeah. I should mention one thing. This is kind of an interesting thing. So it goes like the surface. Yeah. I can give you a chance to stand up too. So this goes like the surface stress divided by R, right? If you say that the surface stress is about equal to the surface tension, typical surface tension, like 1 joule per meter squared, kind of an interfacial energy, 1,000 millijoules per meter squared. You notice this goes like 1 over R. So I can always choose an R small enough such that these stresses can be big due to this thing, right? So if you took a droplet or a particle that's on the order of 10 nanometers, 5 nanometers in diameter, with those kind of interfacial energies I just gave you, the stresses inside could be on the order of a gigapascal. So even though this energy is the surface stresses are very small, if I'm allowed to choose R small enough, these stresses can be big, gigapascals. And so these large stresses might be affecting the stress field in the system. In fact, if you look at nanoparticles, if you measure the lattice parameter of nanoparticles, they're not equal to the lattice parameter of a bulk material because of this effect here. Okay, so they can become important as well, but typically they require relatively small objects, but they can be important. So we'll put that in as a source of stress. Okay, questions? Yeah. Yeah.
So that would be some a partial lattice planes which is not complete.
Right. Yeah, that's a good point. So you make them small enough, eventually this whole idea of coherency, these continuum models might break down, and so that's certainly a possibility. Yeah. Yeah, the nanoparticle case I was talking about was really a solid nanoparticle in a vapor. But still, your point's well taken. I mean, that's certainly possible. And you can ask the question, how big is the surface stress of a coherent interface? And I don't really know, but we'll see. But I don't think people have really measured it well. The reason why it's important in the context of phase field models is that, remember, when you have a phase field model for a coherent precipitate and you have a variation of an order parameter or a composition through the interface, the question is does that variation generate excess stresses associated with the interface? And so I wanted to introduce this surface stress argument here, so you have that as a background. Okay, so if you write this equation here in spherical coordinates, I didn't do this, I looked it up. Basically, we're going to assume spherical symmetry. So the displacement vector is just going to be equal to u times r hat. So it's only along the radial direction. And this is why this problem becomes really so simple. So you get that complicated differential equation that I showed you before, Navier's equation, is really simplifies down to just equals 0. So that has to be satisfied for elastic equilibrium. And you get that u alpha, evaluated at the surface of the particle, has to be equal to u beta, evaluated at the surface of the particle, and TRR beta. R, the limit of so the displacement as you go to infinity has to go to 0 too. And so that's just a second order differential equation where we solve. So this holds both in the particle and outside the particle, because that's just elastic equilibrium. That has to be the case. And so you solve it first in here and then out here, and then using these boundary conditions, you'll be able to solve the elastic field every place. And so that's what we're going to do for the next. We're done at 1, right? Yeah. So I think we'll do this. So you can rewrite the equation for u like this. So it actually looks like d by dr equals 0. That's another way of just rewriting that equation. The reason that's nice is that it's obviously clear how to solve that equation, that differential equation, by integrating that once. R squared. A prime's a constant. And then you can integrate it again pretty clearly, right? And so you end up with it's going to be equal to A over R. So I'll just throw the 1/2 into the constant to redefine it. Plus B over R squared, where B is a constant. And so that's a general solution for Navier's equations in spherical coordinates. And now let's look at now let's begin to apply this. So in the particle, U of R has to be finite at the origin, and R is equal to 0, which implies that B has to be equal to 0. And outside, in the matrix, U at infinity has to go to 0, which implies that A has to be equal to 0. And so you know already that U beta is going to be equal to AR, and U alpha is going to be equal to B over R squared. And so in the outside, the displacement is going to decay like 1 over R squared. To determine, so let's go back here. So we've used this condition and that condition, and we still have to determine A and B. And we have two equations, here and here, to determine A and B. To apply this condition here, we need to express TRR in terms of U. And then we can apply that condition, right? So we know from our trusty continuum mechanics books that and E theta theta is equal to E phi phi. It's going to be equal to U over R. Again, that you have to write that out, write the tensor out in spherical coordinates, and then just take the R hat quantities. Okay. So one thing that I have to take a kind of an important detour on is I have to explain eigenstrains or these misfit strains. And this is the thing that if you've never seen this before, always confuses students. It's not something that's really kind of obvious to us to the first time you see it. So let's go back to this here. So when I took now we're going to try to describe this whole process that I showed you here mathematically. And what you do is when you go from here to here, right, you're applying a strain. Epsilon ij, right? And so you apply a strain on going from here to here. And then when you put it back into the matrix, you have a relaxation from that state out. And so you have some elastic strain in the system too. And so you have this is the eigenstrain here. You have elastic strain here, the elastic. And what you want is that as you go from that you want this whole process to be such that the material doesn't fold over on itself or doesn't create any gaps. And so the way you say that is that you want it to be coherent or compatible, is what the continuum mechanics folks would say. And so the total strain in the system is equal to the elastic strain plus this eigenstrain. So remember the elastic strain. So the eigenstrain is taking that thing, compressing it, putting in, and then you have some relaxation on top of that. And so you sum the two together, and that's the total strain. These things that are related to the, so that means that Tij, which is going to be equal to, I guess it's easier to write it like this. And then beta, this is in the beta phase, is equal to the elastic strain. And so this is going to be related to okay? So it's going to be related to the difference between, that's just Hooke's law, right? Elastic strain times elastic constants gives you stress. This over here is what happens when you have an eigenstrain or a misfit strain. So this is the total strain, remember? It has to be compatible. And that's the eigenstrain. And so you see you have this minus sign there, right? You have the minus sign. And that's because we're using the alpha phase as the reference state for strain. Basically, we're measuring that relaxation, the elastic strain, relative to the alpha phase. And someone already corrected me on my definition of the misfit strain, right? The reason why the alpha sits in the denominator is because we're using the alpha phase, the matrix phase, as the reference state for strain. The thing that has to be compatible, since Eij has to be EKL has to be compatible, what that means is that this is the thing that's related to gradients in the displacement. Material. And so that means that Okay. Looks like that. So the factor of 2, where did the factor of 2 go? I think I heard someone mention that. And it has to do with the symmetry of the elastic constant tensor, because these are implicit summations, and the elastic constant tensor so you can interchange L and K and L. And so if you substitute this into here, you can see that this is just an interchange. If you substitute this into here, you see you're just interchanging L and K. So you basically lead to the same term. So they sum together, and the 1/2 disappears, and you can write it like that. Okay. So if you wrote this for in spherical coordinates, yeah, let me write it out for an isotropic material first. So you get Tij is going to be equal to yeah. Let me write this. Let's go back and rewrite this equation in spherical for an isotropic material. Kk beta plus 2 mu Ij beta minus 3 times the bulk modulus beta epsilon delta Ij. So basically I'm writing this this equation here, right here, okay. So do I have to include an eigenstrain in the alpha phase? Do I have to include an eigenstrain in the alpha phase? No, right? Because there's no eigenstrain in the alpha phase. It's only in the beta phase. So that's it for the alpha phase. K beta is the bulk modulus. Beta. So basically, if you put oh gee, sorry. So if you put this equation into here, and you took the elastic constant tensor for an isotropic material, contracted it with the delta function here. So delta is equal to 0 if k is not equal to L, and is equal to 1 if k is equal to L. You get the bulk modulus after you do that contraction. Okay, so let's write this in spherical coordinates. So you have TRR. It's going to be equal to lambda plus 2 mu epsilon. So the Ij becomes, so you know, Ij can take off. So we're looking at TRR. So you get ERR, which is what this is. And this is the trace. So it's E theta theta, E phi phi, and ERR. And then if you put the definitions of the displacements in terms of these strains in the equation, you get ERR is equal to du dr beta. And these two things are exactly the same. So it's just 2 mu beta over r. So they sum together. Epsilon. And so now what you can do is just go back. Now it becomes kind of simple. So now we know what the displacement field is in the beta phase. It's just A times R. And so you just substitute that in. It's going to look like A times R. So the derivative of that's just A. Plus A times R, so the R's cancel. Epsilon. And so this becomes A minus epsilon, because the bulk modulus as the definition of the bulk modulus in terms of those other two elastic constants. There are only two independent elastic constants for an isotropic material. In the matrix phase, you have TRR alpha the same equation that we had before from up top, except without the eigenstrain. And now TRR alpha looks like this. It's B over R squared. B over R squared, so that'll be minus 2 B over R cubed plus 2 B over R cubed 4. Minus 4 mu alpha B over R cubed. So this is equal to 0. So that goes out. And so you have TRR evaluated at the surface of the particle. It's just given by minus 4b mu alpha over R cubed. And so notice the trace of the stress, the trace of the strain disappears here. And so now you can put this into this condition here. And that's just algebra. So you basically end up with an equation that involves both B, 4b cubed plus 3k beta epsilon is going to be equal to minus 2f over r. And then if you then use the displacement condition, that u at alpha at r, at beta at r, and so that means basically that AR is going to be equal to B over R squared, which implies that B is going to be equal to AR cubed. Okay, and so now this is from the force balance. That's the force questions. That's the force balance. Questions? That's the displacement condition. And so you have two equations and two unknowns for each of the A's and the B's. And the results are that A is going to be equal to 3 epsilon F over R divided by alpha. And that B is therefore just A times R cubed. Okay? Questions? Okay, so so now we can just now we can evaluate the stresses and strains. So in the particle, is equal to A TRR is equal to 3K minus epsilon. And in the matrix, ERR and E theta theta by spherical symmetry. This has to be the case. Cubed. And TRR or R cubed. Cubed. And A is just this. Plus 4 mu alpha. Note yeah. Say it again. Yeah. So what I did what I did here. So that's a good question. So here these are general results. So if small r is equal to capital R, those cancel and you get minus 2a. So they get the value at the interface. Yeah. So let me kind of step back. So basically, I wanted to write these out, and this is just algebra once we get to this point, and talk about some of the physics of this. So you can see that the stress field falls off like 1 over r cubed from the particle. So it falls off very, very quickly, reasonably quickly. It's not like 1 over r. It's not like a long-range Coulombic decay. You'll notice that the trace of the stress is 0 inside the particle, and the trace of the stress in the matrix is 0. In the particle, it's non-zero. So remember, what is the trace of the stress? What is the trace of the stress? It's like a pressure, right? Hydrostatic pressure. Yeah, great. So the hydrostatic pressure in the matrix is 0, and in fact, you can kind of see that it's. You see, everything here depends upon the shear modulus. Everything depends upon the shear modulus, and so it's under a state of pure shear, actually. And so let me talk about some of this. So we have the misfit strain is you can write it in terms of molar volumes of lattice sites if you wanted to, like this. Sorry, yeah. That's right. There's no shape change. Yeah. So we'll talk about shape changes is a big question. Is a big issue. So this is assuming that you have a spherical particle. Okay. So you're asking a deeper question is, if I allowed for shape changes, would this be an minimum in the energy? That's a different question. In fact, it's probably not in some cases. Yeah. Okay. So let me just talk about the stress states for a second here. Let's talk about the beta phase. The stress field and strain field are constants. Look, if you don't believe me, that's really weird. The stress strain inside the particle is independent of position. It's independent of position. It certainly varies with position outside the particle. Goes like 1 over r cubed. Inside the particle, it's a constant. And you'll note that TRR beta, T theta theta beta, and T phi phi beta are exactly the same. And so that means that it's pure hydrostatic stress. Oops. So it's just like it's under pressure in the particle here. So let's look at, so that's one important thing. And if we want to talk about the generalities, you can generalize this problem to ellipsoids. And the amazing thing about ellipsoids is the stress inside an ellipsoid is still a constant. Yep. It's always hydrostatic. And so let's talk about exactly that question. So let's look at some limits. So A here. So A is dependent on both. So here's A depends upon both the misfit strain and the surface stress case. So let's set the surface stress to 0 and just look at what this tells us. So in this case, let's say that F equals 0. Oops. Equals 0. So A is going to be equal to 3k beta epsilon plus 4 mu alpha. So the strains inside are related to both A and epsilon, and you can see that A is negative, and the term involving A is positive. That's negative. So if you work, So if you work this all out, TRR is equal to minus. If you plug in the value of A and simplify things, that's what it looks like. And so if epsilon is greater than 0, TRR is less than 0. So that kind of makes sense, because if the molar volume of beta is greater than the molar volume of alpha, it's basically under compression. Kind of what you'd expect. If you consider the case that was kind of asked before, where F is not equal to 0 and epsilon equals 0, so this is the case where you only have surface stress, then A is going to be equal to minus, 2F divided by R, and TRR F over R. And so the pressure times kind of as you'd expect, that the pressure inside is going to look exactly like what you get. Basically, it looks exactly like the Laplacian equation, assuming an F equals sigma. Okay. And so this fact that A is present in this system means that you can see it involves both the surface stress and this thing. And so if the 2F over R is comparable to k beta epsilon, then these surface stress terms can be just as important as the misfit strain terms. Okay. So if you look at the matrix phase, the stress is equal to 0, and that means it's under pure shear. Okay? And so you have this very strange situation where you have a beta particle and alpha, not strange, but interesting situation, where in here, it's under pure hydrostatic stress, whereas out here, it's under pure shear. And so the way to kind of understand what's going on here is that if you had a particle here and it relaxes out to here, so this is the relaxation process, it relaxes. What it does is that it introduces pure shear. In other words, the matrix kind of wants to slide against one another like this, and it's bigger at the interface, and it decays, and so it basically pushes out, and the structure, the matrix wants to slide like this. It doesn't go out uniformly; it actually slides. Wants to slide. It doesn't actually slide, but it gives rise to a shear stress, and so you have pure shear out here, and it's constant in here as well. It doesn't vary with position, and this is why I think sometimes these elasticity problems, at least to me, are pretty non-intuitive, because you have a hydrostatically stressed body so you just take a particle, you put it in, and it's a hydrostatic stress, a pure dilatational misfit, and you get a hydrostatic stress inside and shear going away. So you can see that the other thing I want to point out is, look at.
There is a particular particle size so that these two will cancel.
They cancel with the right sign of the surface stress. Yep.
Then what happens?
Then you have a stress-free system. Yeah, that's right. So if epsilon's positive and your surface stress is positive, if you can find an R where that term.
So if that happens, for example, that system will just stay there forever?
It'll be stress-free, but it'll only be stress-free for a particular size, right?
Particular size.
Yeah.
So I'm saying that if you, for example, will go from some other size to that size, then everything will stop.
Yeah. The stress will be 0, right? Yeah. And so it's the way the surface stress, one is pushing out and the other is pushing in, and they balance exactly the right place.
Stress equal to 0 mechanical.
There's lots of generic issues, interesting problems associated with this. So you can see that let's look at T theta theta. So this is the stress in the theta direction, which would be this way, parallel to the interface, right, as you go across. So T theta theta, theta plane, theta direction. So it's parallel, tangent to the interface. And so it varies with position outside the particle. And you can see once you go inside the particle, it's a different value. So if you evaluated this at capital R, those would cancel, would be A, 2 mu times A. Inside, it's 3K beta A times epsilon. And so you can see that the T theta theta and T phi phi actually jump at the interface. They're discontinuous. So at the particle matrix interface here, T theta theta and T phi phi jump at the interface as you go across. TRR also jump if the surface stress is non-zero. But if the surface stress is non-zero, TRR is continuous because of the force balance. But the T theta theta can jump. Okay, and so now the whole audience here is thinking phase field, right? So if this is a phase field model, and you have this jump, you're doing exactly the same thing that you did to the jump in concentrations across the interface in the Cahn-Hilliard model. You're going to replace this with a smoothly varying function as you go across. So you're taking this jump and replacing it by a smoothly varying function, and then you can ask all the questions we asked, right? Is this sharp interface model, the black, and the diffuse interface model, the red, that you get from the phase field model, is it going to give you the right stresses at the interface when you have this jump here? Okay, so that's why this is an important base. This is an important sanity check on your phase field code. So I want to kind of put this into context. So what we've done is a linear isotropic elasticity, where we've allowed mu alpha to be different than mu beta, and k beta to be not equal to k alpha. So in other words, there could be differences in elastic constants, and we've assumed all of this, and we get these kind of interesting results that it's hydrostatic stressor, it's constant. It turns out that this also holds for ellipsoids. So if you have difference in elastic constants, you also get a constant strain inside the particle and a strain outside that varies. Kind of amazing. In ellipsoids, not spherical shapes, in ellipsoids. And this goes back to some work by Eshelby.
So Peter, why if PKK is 0, that is pure shear?
There's no hydrostatic stress. There's no hydrostatic stress, so it's got to be shear.
It can be a radial. Just the trace which is 0.
The trace is 0, right? Yeah. Here. Okay. Yeah. So those things do vary, as you can see, with R.
I mean, in the graph you showed, the lower graph next slide.
This one. Yeah.
Still have a radial.
Yeah, that's right. Yeah. But the trace of the stress is always 0. So this is an interesting kind of okay. So the reason, one of the reasons what to emphasize this is kind of an interesting sidelight, right? So if you think about the thermodynamics of fluids is always associated with pressures, right? PDV terms. Here you have a matrix that's under pure shear that clearly has energy associated with it, but it's not PDV energy. It's strictly the shear energy. So you have to do the full elasticity for this, full elastic energy to get that right. Yeah. So it's and in fact, since the trace of the stress is 0 outside a spherical particle, it doesn't generate any diffusion fluxes typically because those depend upon traces of stress and things like that. It's kind of a very unique and interesting limit. Okay, it's a very simple limit. So this also holds for ellipsoids, and that goes back to Eshelby. And the amazing thing is that even if it's elastically anisotropic, it still also holds. So spheres and ellipsoids are really special objects. If you depart if it's non-spherical or non-ellipsoidal, all of these ideas of constant stresses inside the particle and things like that break down and don't occur. Not the case. So okay, here this kind of related to what Guru's question we were just discussing. So if you look at the equations for the matrix phase out here, right? And so the picture here is you put this particle in, it relaxes, it pushes back out on the matrix, right? Okay, so let's say that the matrix out here is a fluid. What's the shear modulus of a fluid? 0. So if you take a shear modulus of a fluid being 0, that's 0, that's 0, you have no stress in the matrix. And so the fact that you have a non-zero, so it really is a state of pure shear. that in fact there's no stress left in the matrix. If you go into the particle, the shear modulus equals to 0, right? So you only have the bulk basically it's the bulk modulus divided by F, which gives you the stress. So you kind of go back to the fluid case, but the fluid basically in this case has 0 pressure because the shear modulus is 0. Okay, so it all kind of fits together. So if you have a fluid model, you have no shear stress, you have no elastic energy, and you get basically nothing going on in the matrix. Okay.
Stress remaining inside the particle.
Yeah, I know you're going to ask that question. So let me think a bit. So what you get, so if this goes to 0, yeah, so if this is 0, that disappears, this cancels, and you still have this epsilon term. So you put this into epsilon, the epsilons cancel, and you get 0 stress. Okay, so you have no misfit stress. Okay, so yeah, okay, it works. So you set that to 0, and say F is equal to 0, so that's not there. The K betas cancel, the epsilon comes over to here, cancels here, and you get 0 stress in them. And the other thing I want to point out as well is if you look at the stress in the matrix phase, if you let F be equal to 0, it depends upon the sign of epsilon. So whether ERR is positive or negative depends upon whether you have epsilon being positive or negative. And so it captures a lot of the basic physics and ideas of what's going on in the stress problem for particles. And now you've done the case where you have very small particles. So you can go back and you claim that you're doing nanomaterials if you wanted to keep your sponsors happy. So, okay. Any other questions? We're at 1 o'clock. That's great. Worked perfectly. Very good. Okay. Thank you. I'll see you this afternoon at 2. 2:30. 2:30. Okay. See you at 2:30.